This video is dedicated to Jack Scully, who complained that my videos were too slow. Play this at double speed in YouTube and it should sound normal. Okay, moving on. Chapter 18 starts with a discussion of counting when it comes to really small, tiny objects, namely atoms and molecules. So here are some non-numerical terms for common numbers. Here you've got a pair of vases, that's two. A dozen roses, I mean, that's the same as 6 twos, but it's easier to say a dozen. There are a dozen roses here, I checked. Or you could say 12 dozen eggs. 12 dozens, a little wordy. So they have a word for that too. This is called a gross. The gross of eggs is 12 squared, 144. And then we'll jump to the big number, the number of atoms in this little pile of carbon dust. You'll notice on the scale it says that pile of dust weighs 12 grams, or it's got a mass of 12 grams. And somebody a long time ago, probably some lowly graduate student who had nothing better to do, he was tasked with, he or she was tasked with counting the number of atoms in this little pile. It took them a long time to count because they had to take a pair of tweezers, grab an individual atom, set it off to the side, grab another atom, set it off to the side. And a few times he was halfway through the pile and somebody knocked on the door, distracted him, or his phone rang, and he had to start all over. But eventually he got up to the total count, and it turns out to be 6.02. Take that decimal point, move it to the right 23 times. Took him a long time to count that number. Of course, that's not how it was done. Your book doesn't actually describe the way in which this number was determined. I think a variety of experiments have been done to determine that number. That number is called Avogadro's number. I'm sure you've seen it before. There's even like a Schoolhouse Rock type video out there that helps you remember this number. You probably should commit that number to memory. So there are some ingenious experiments for pinning that number down. It's a really, really big number. So 1 mole, by definition, and keep in mind that it's often abbreviated MOL, but the full word is MOLE. It's that number right there, Avogadro's number. And if you look it up on Wikipedia, they do know this number to more digits than just 3. This is also 1 mole, but that's not the definition of the mole that we will be working with. This is our definition for chapter 18. Outside physics, this would be 1 mole. You should probably memorize that the definition of a mole is the number of carbon atoms in 12 grams of carbon, specifically carbon that has 12 so-called nucleons. Remember the nucleus of an atom, you've got your protons and your neutrons. Both of those are nucleons. All carbon has 6 protons, right? That's what makes it carbon. If it had one more proton, it would be nitrogen, not carbon. So having 6 protons is what makes it carbon, but you could add a few extra neutrons in there and it would still be carbon. If it's got 12 total protons and neutrons, that means 6 protons, 6 neutrons. That's the most common type of carbon in your body. There is carbon-14 in your body as well, 2 extra neutrons. But anyway, the definition of the mole is the number of carbon atoms in exactly 12 grams of carbon. And you can imagine that's a really big number because atoms are small. You can feel the weight of 12 grams. Put that in your palm, you can feel it. And atoms are super small, so there have to be a whole lot of atoms so that they add up to something heavy enough that you can feel. Okay, here's a little cartoon picture of a carbon-12 atom. 6 protons, 6 neutrons, and as I said a moment ago, a proton or a neutron, those are both examples of something called nucleons. There's the spelling there. Not nucleons, nucleons. Then you've got these little electrons buzzing around in orbits. That's the old classical picture.
later. There's a much richer, sophisticated picture of atoms that we have now ever since the 1920s. That's a topic for later in the semester. Probability waves. For now, you can think about them as being in circular orbits. You should know that they're teensy-weensy compared to the nucleons. Here's a pretty accurate number, 4 sig figs. I just remember basically 2,000. A nucleon is something like 2,000 times as massive as an electron, which means when you're talking about the mass of an atom, if you're just being approximate, you can completely disregard the electrons themselves. And I want to make sure that I'm recording. Yes, I'm recording. Okay. Now, there's one way of thinking about this that your book doesn't actually come out and say. They kind of flirt with this concept, but they don't state it. So I'm putting this in the video because I think it'll help you. Just pretend that I've drawn 1 mole of carbon atoms here. Of course, I've only drawn, what is that, 18? Let's just pretend it's a mole. Again, 1 mole of carbon-12 has a mass of 12 grams. What would happen if you replaced each of those carbon atoms with a single nucleon, as I've done here? So instead of a mole of carbon atoms, for instance, you're looking at just a mole of protons. Yes, there's an electron too. So technically this would be which atom? The simplest of all atoms, the hydrogen atom. So you could also down here, instead of saying a mole of nucleons, you could say a mole of hydrogen atoms. Let me back up again. If a mole of carbon-12 has a mass of 12 grams, then what would the mass of a mole of just nucleons be? You see that would just be 1 gram. Think about that for a second. I would just memorize that because it's a very useful fact. If you have a mole of nucleons, they weigh 1 gram. That can't be a coincidence, right? They chose to define the mole in this manner, so you'd have that convenient conversion factor. Okay, now I put basically here because there is a subtlety there, which I'll get to in a moment. But try to remember that 1 gram, that's the mass of 1 mole of nucleons. Now, it's not exactly that because let's just pretend that this is carbon. Well, or not. Here's an atom with 6 nucleons. Is it 6? That looks like 7. Yeah, here's an atom with 7. So this would be a nitrogen. 7 nucleons in the nucleus. And imagine busting that thing up into little pieces. All right. Well, it's a little surprising that if you take all these and add them up, they actually have more mass than they do when they're stuck together. That's a bit of a head scratcher if you haven't studied that yet. So if you, here the arrow is going from left to right, but if you go from right to left, what if you could take these 7 nucleons, squish them together? I'm sorry, that would not be nitrogen. I misspoke. Nitrogen has 7 protons and often 7 neutrons, which would be an atomic mass number of 14. I goofed that up. I'll be honest, I don't actually know which atom has 3 protons, right? If the blue ones are protons, I don't know. What is it? Hydrogen, beryllium, lithium? I probably skipped one. I just laid bare my ignorance of chemistry. In any case, when you take these 7 nucleons and squish them together to make a nucleus, what you get weighs less than the sum of its parts, which indicates what? Some of that mass just disappeared. Where did it go? I mean, how could you end up with less mass than you started with? Well, you've heard of Einstein. You've heard of E equals mc squared. There's a whole chapter in your book called Relativity, which we don't have time to cover this semester, but E equals mc squared is all about how mass and energy are equivalent. That little piece of mass that disappeared when you go from right to left, it shows up as a tremendous amount of energy. mc squared, where c is the speed of light. It's a huge number already, c. And when you square it, you get an even bigger number. Well, that's the energy that's unleashed when you fuse atoms together in a fusion bomb. Just a moment ago, I said, imagine taking these nucleons on the right and fusing them together to make a nucleus. In the act of fusing nucleons, very often a tremendous amount of energy is released. That's what's happening in a nuclear warhead. This is probably some old photo from the 60s because they don't test those anymore. Oh, look at these poor Joshua trees down here. I live up here in the desert now with Joshua trees everywhere. And did you know that these trees, they only grow something like 1.5 inches a year? When they reach maturity, 1.5 inches a year. So if you see a Joshua tree that's 20, 30 feet tall, do the math, that thing's as old as America. There's all kind of trees like that around here. Okay, that's also the source of energy in the sun. The core of the sun is nuclear fusion. So you've got mass being converted into energy. All right, that's not so much the topic of this chapter. Some nomenclature here. Your book reserves the letter lowercase m for the mass of an individual atom. So we're talking about a very small number in kilograms. Big M is, I goofed that up. Let's look at this slide instead. Big M sub mole, that's the mass of 1 mole. Well, that's going to be a bigger number. So what's the mass of 1 mole of carbon? 12 grams. So that's an everyday amount of mass, something you can actually feel in the palm of your hand. Capital M without the subscript, that's the mass of your total sample. Maybe you're looking at 20 pounds of carbon. That would be capital M, would be that mass, and you can figure out how many moles were in that. Okay, lowercase n is number of moles. That's always going to be the number of moles in this chapter. Big N is reserved for total number of atoms. So in general, big N is an enormous number, something like 10 to the 23rd, 10 to the 25th, etc. Whereas lowercase n could be a dozen. So the number of moles of air particles in the room that you're sitting in right now, it's, I don't know, 100 moles maybe. But the number of atoms, it's got to be something like 10 to the 30th. 10 to the 28th. Okay, if you take the number of moles that you're dealing with and multiply by how many particles are in a mole, that will give you the total number of particles. This is an equation you should be familiar with. So now, with those basic facts, we can do a little bit of math here and answer an interesting question. If you take 1 cubic millimeter of copper, and I chose the most common isotope of copper, I had to Google that, I'm not a chemist. I should have pointed out that this number in the upper left, this is called the mass number or the atomic mass number. The mass number tells you how many protons plus neutrons are in the nucleus. So there's a total of 65 protons and neutrons in the nucleus of this particular isotope. Remember, you could squeeze a couple extra neutrons in there and you'd have something like copper 67. I'm talking about copper 65. Consider just a tiny little cubic millimeter of copper. Just how many atoms are in there. If you tried to make a guess about this when you were in high school or junior high, you probably way underestimate the number because we're not born with any intuition about just how small atoms are. So let's look at this box here, 10 centimeters by 10 centimeters. 10 centimeters, that's a little shorter than a ruler. Chop that into 10 pieces and zoom in on that. So here's 1 cubic centimeter, also known as a milliliter. Chop that into 10 pieces, lengthwise at least. So one of these teensy-weensy little cubes, that's a cubic millimeter. You can barely see that, right? If you've got it, if you pinch that between your fingers and held your arm out, you can barely see that. It's a very small piece of matter. Let's figure out just how many atoms. Well, you can look this up in a table or measure it yourself. If you happen to have 1 cubic meter of copper, that's a lot of copper. That would be very valuable. I would be nervous to have that in my possession because somebody would break in my house, probably would steal it. But it's an experimental fact that 1 meter by 1 meter by 1 meter solid chunk of copper has a tremendous mass of almost 9,000 kilograms. I'm going to move to the next slide. All right. Each atom of copper 65, what's the significance of that 65 again? It means it's got 65 nucleons in it. Well, remember, 1 mole of nucleons is 1 gram. 1 mole of copper atoms would have 65 times as many nucleons. So there you go. It's got 65 grams of mass. It's you just have to remember that a mole of nucleons is 1 gram of mass. Okay. Let's do some conversion here. Let's see how many moles are in this cubic meter chunk of copper. So ask how many times 65 grams right here divides into 8,960 kilograms. And that'll tell you how many moles are in that big box of copper. I like to try to think about this conceptually, but also know how to set it up with the conversion factors. You should do the same thing. Get good at multiplying these conversion factors together. You can see how kilograms cancel, and we'll have moles per cubic meter. Okay, it's still a big number, but it sounds about right. I mean, if 1 mole of carbon is only 12 grams, there should be a whole lot of moles of copper in a chunk that big. Okay, let's convert that now into number of atoms. If there are this many moles in this box of copper, and each mole has this many atoms in it, then we're talking about a whopping 8 times 10 to the 28th particles per mole. And you'll notice I didn't write any units here. Your book talks about this because particle is not really a unit. You know, whether you're talking about pencils or roses or aces, that's not really it doesn't have any dimension. So we just leave it dimensionless. So I just determined that there are this many atoms of copper per cubic meter. Capital N is the total number of atoms, remember? V for volume. So this is what your book calls number density. In SI units, it's a tremendous number, 10 to the 28th. SI units because the unit of volume in SI would be the cubic meter. There's a lot of atoms in a cubic meter. The original question that I was asking was, how many atoms are there in a cubic millimeter? That's a little easier to wrap your head around. So let's convert from cubic meters to cubic millimeters. 1 meter cubed, that's 1,000 millimeters cubed. So I really have 9 zeros down here. Do I? 369? Oh, this came out wrong, didn't it? Shouldn't that be 10 to the 21st? I'll check that on my calculator right now. Put that into the camera. I don't need to check it. Of course, there's 9 zeros down there. All right, I goofed that. I suppose that should be 8 times 10 to the 19th. I'll have to fix that. Anyway, Chris Farley's impressed. That's a really big number.